Welcome to Study Loop.
So in first part of the problem, we have to calculate the initial pH. That means the pH of the solution before the addition of the base. So since the acid present here is a weak acid, that is acetic acid, so it being a weak acid, we need to find out how much H plus ion will be generated in the initial solution, and for that we need to set up a reaction of acid with the water. So that will be HC2H3O2 reacting with the water, and we will get H3O plus and C2H3O2 minus. Now, so our the initial concentration of acid is 0.105, and our initial concentration of the H3O plus is 0. Also, the initial concentration of the acetate ion is also 0. Now, if we assume that X molar H plus ion are produced, or H molar of the acid is being dissociated, then we subtract X from here and we add X molar H3O plus and X molar acetate ion. So in the equilibrium of this reaction, we will have 0.105 minus X molar acid, X molar H3O plus, and X molar acetate ion. So from here, we can set up a relation between the Ka value with the product concentrations on top over the reactant concentration, that is H3O plus concentration times C2H3O2 minus concentration over HC2H3O2 concentration. So, and as we know that the Ka value for the acetic acid is 1.8 times 10 to the power minus 5, and on the product side both of these have uh, the concentration of X, so we have X square on the top, and in bottom we have 0.105 minus X. Now we can ignore this X being very small compared to the 0.105 molar concentration, and if we solve this equation for this X, we'll have a value of X as 1.37 times 10 to the power minus 3. So this is the initial concentration of the H3O plus ion produced. That means the pH, or the initial pH, will be the negative log of this value here, and this will give us a pH of 2.86. So this is the initial pH of the solution. Now in part B of the problem, we have to find out the volume of the base added to reach the equivalence point. We can find that by simply applying the M1 V1 is equal to M2 V2 formula, where M1 is the concentration of the acid, V1 is the volume of the acid, M2 is the concentration of the uh, base, and V2 is the volume of the base required to reach the endpoint. So from here, the volume required will be the concentration times the volume of acid, which is 0.105 molar times 20 milliliter over M2, which is the concentration of the acid, 0.125 molar. So from this calculation, we will have a volume of 16.8 milliliter. So this is the volume of the base required to reach the equivalence point. Now in part C, we have to find out the pH after the addition of 5 ml base. So for that, first we have to know um, the number of moles of the acetic acid. Then we have to calculate the number of moles of sodium hydroxide in 5 ml volume, and then we have to set up the reaction between the sodium hydroxide added with the acid. From there we will have to uh, plug in the final number of moles in the Henderson-Hasselbalch equation to find the pH at that point. So let's start with finding the number of moles of acetic acid. So the initial number of moles of acetic acid moles of the acid is basically the concentration of the acid times its volume, which is 20 milliliter or 0.020 liter, and this will give us 2.1 times 10 to the power minus 3 mole. So this is the number of mole of the acetic acid. Now we have to find out the number of moles of base in 5 ml, because we are adding 5 ml of base at this point. So we have to multiply the concentration of the base, which is 0.125 mole per liter, times the volume, which is 5 milliliter or 0.005 liter. So from here we will have the number of moles of base as 0.625 times 10 to the power minus 3 mole. So this is the number of moles of base in 5 milliliter. Now we have to set up the reaction that will occur between the added base and the acid. So we are adding here sodium hydroxide to the acetic acid, and we are producing sodium acetate and water. So now our initial concentration of the acetic acid is 2.1 times 10 to the power minus 3. Now we are adding 0.625 mole base. That means this much base will react with the same amount of acid. That means it will subtract 0.625 mole from the acid, and it will add 0.625 mole sodium acetate. So in the resulting solution we will have and the number of moles of acid as the subtraction of these values, which is 1.475 times 10 to the power minus 3. Now we know the number of moles of acid after the addition of 5 ml base, and we also know the number of moles of base. So if we just plug in these values in the Henderson-Hasselbalch equation, we will be able to find the pH at this point. So according to Henderson-Hasselbalch equation, pH is equal to pKa. So the pKa for acetic acid is 4.74 plus log of base concentration over acid concentration, or we can write it moles of base over moles of acid if the volume for the base and acid are same. So we have moles of base over moles of acid, and so if we just plug in the moles of base and moles of acid here as these values, we will see that and the pH will be 4.37. So this is the pH of the solution after the addition of 5 ml base. Now in part D, we have to find the pH at 1/2 of the equivalence point. So since it's a weak acid strong base titration, in such cases the pH at half equivalence point is basically equal to the pKa of the acid. So here our pH is equal to pKa of the acid or the acetic acid, which we already have seen that is 4.74. So this will be the pH at the half equivalence point for this titration. Now we have to calculate the pH at the equivalence point. So at the equivalence point, the pH of the solution will be due to the reaction of the acetate ion with water. So first we have to calculate the concentration of acetate ion in the flask at the equivalence point. Now to find that, we have to um, know the number of moles of acetate ion at the equivalence point. So since at the equivalence point the total acetic acid will be reacted, that means the concentration of acetate ion or the number of moles of acetate ion at the equivalence point is the initial number of moles of acetic acid, which is we have already calculated as 2.1 times 10 to the power minus 3 mole. So this is our number of moles of acetate ion. Now we have to find the concentration of acetate ion at the equivalence point. So we have to divide these moles by the total volume of the solution at equivalence point, which is we already had the acid solution as 20 ml, and to reach the equivalence point we have added 16.8 ml of the base. That means in total we have 36.8 ml or 0.0368 liter in volume. So apparently the concentration of the acetate ion at the equivalence point will be 0.0571 molar. Now, as we have said that at the equivalence point we will have the reaction between the acetate ion and the water. That means let's set up the reaction. The acetate ion this will react with the water to make an equilibrium between or with the acetic acid and OH minus ion will be produced. Now, so at the equivalence point, we have seen that the concentration of acetate ion is 0.0571 molar, and at that point we have 0 molar acetic acid and 0 molar hydroxide ion. Now, so if we assume that uh, x molar of the acetate ion will react with the water, we subtract x from here and we add x mole acid and x mole hydroxide ion. So in the equilibrium of this reaction, we will have the acetate ion concentration as 0.0571 minus x, and x molar acid and x molar OH minus. Now, so since here we are producing hydroxide ion, we have to set an expression for Kb value. So the Kb will be the product concentrations over the reactant concentration, and here we have both of the product concentration as x, so we will put x square over the reactant concentration, which is 0.0571 minus x. Now we don't know the Kb value here, but we know the Ka value for the acetic acid, which is 1.8 times 10 to the power minus 5. So here's the relation between K and Kb, which is Kb is equal to Ka over Kw. So our Ka value is 1.8 times 10 to the power minus 5 for the acetic acid, and Kw value, as you know, it is 1 times 10 to the power minus 14 as always. So from here we can find that the Kb value for the reaction we are talking about is 5.6 times 10 to the power minus 10. So this is our Kb value. So if we just plug this value here, and if we ignore this x being very small compared to this value, and we solve the equation for this x, the value of x will be 5.6 times 10 to the power minus 6. So this is our OH minus concentration. So to find the pH, we have to know the H plus ion concentration, and as we know again that the relation between H plus and OH minus is simply Kw over this OH minus concentration, and again Kw value is basically this value. So if we put this value over the OH minus ion concentration we have just found, we will have the H plus ion concentration as 1.77 times 10 to the power minus 9. So this is our H plus ion concentration, and from here we can find the pH by taking the negative log of this value, which will give us a value of 8.75. So this is the pH at the equivalence point of this titration. And finally, we have to calculate or find the pH after adding 5 ml of base beyond the equivalence point. So for this part, we have to first know the number of moles for 5 ml sodium hydroxide. For that, we just simply multiply the concentration of the base with 5 ml or 0.005 liter, and here we will have the concentration as 0.000625 mole. So this is the number of moles of the sodium hydroxide for 5 ml. Now, so uh, now we have to find the concentration of the excess sodium hydroxide we are adding after the equivalence point. So we'll just find this by simply putting this number of moles over the total volume at the time. So to reach the equivalence point, we have already had 36.8 molar, and now we have added more 36.8 milliliter. Now we have added more 5 milliliter. So in total, we have 41.8 milliliter, or 0.0418 liter. So from there, we will have the concentration of the excess sodium hydroxide we have added here. That will be 0.014 molar. Now, since sodium hydroxide is a strong acid, that means the excess sodium hydroxide concentration will be basically uh, the OH minus 7 concentration at that point. So the OH minus 7 concentration here is 0.014 molar. From here we can find the H plus 7 concentration at that point, which will be simply the value of Kw over the OH minus concentration. That means 1 times 10 to the power minus 14 over this OH minus concentration 0.014, and from this calculation we will have the H plus ion concentration as 6.688 times 10 to the power minus 13 molar. And now just taking the negative log of this H plus ion concentration, we can find the pH at that point, which will be 12.17. So this is the pH after adding 5 milliliter of base beyond the equivalence point.